Motor function. In this video, we'll be breaking down the complex variables that influence motor behavior and performance. Now note, this is probably the most info-dense video we'll come across so far, so feel free to rewatch it and pause it if you need. But here's why this video matters. It's to understand in detail how an e-bike motor works. It's going to help you dispel many misconceptions about e-bike motors and gain an edge in product knowledge. It's also useful for high-performance e-bike tuning and system design. Prerequisite VODs, this video relies upon a lot of prior knowledge from all of these other videos, so feel free to go refresh your memory if you need to. So we're going to divide this video into a few key factors about the motor. The complex part is they all interact and influence each other, so I'll try go through them sequentially, but our knowledge should build up as we get through to the end. I'll be referring to this graph a lot. It's a very useful tool from ebikes.ca, and it's also a great range calculator, so you can scan this QR code and play around with this tool yourself if you want to. So the motor key factors are torque, or the twisting force, power, RPM, load, efficiency, and temperature. Starting with torque, the twisting force produced by the motor in Newton meters or foot-pounds. Now, as we accelerate our e-bike, the torque goes on a bit of a journey. First of all, it starts off flat, which is controller limited, or it might start off as a high peak and begin to decrease. This is the same in all electric motors. That's why you hear the saying you get full torque from 0 k's an hour. But as your RPM, or the speed of the motor, increases, torque begins to drop off. And eventually it might fall off quite sharply. But at a certain point, torque matches all of these resistances and acceleration becomes 0, which means you have reached your top speed. Torque multipliers. Mid-drives have external gear ratios from the bike's drivetrain, aka the bike has gears and you can influence the motor torque by changing them. In our example here, we have two systems which are in a different gear, otherwise completely identical. The first system is in a hill climbing gear at 34 teeth at the cassette, whereas the second system is in a fast gear at 11 teeth at the cassette. To calculate a gear ratio, we just take the output, which is the teeth of the cassette, and divide it by the input, which is the teeth of the chainring, giving us our answers here. And we can see in our graph how that drastically produces different torque curves. OEMs typically rate peak torque at the motor's chainring, if it's a mid-drive, and at the wheel if it's a hub drive. Understanding these differences gives us a little bit more detail, and we can explain to customers that the torque of the bike may depend upon what gear you're in. Let's explore the gear ratios a little bit further. Like the last example, we have two systems running an identical setup in two very different gears, 50 tooth at the cassette versus 11. We can see our peak torque here is 225 Newton meters in the slowest hill climbing gear, whereas in our fastest 11-tooth gear, our peak torque is only 50 Newton meters, whereas the motor in this example is rated by the manufacturer at 160 Newton meters. Now, I've just put this in italics here because if you take 160 and you multiply that by gear ratio, you'd get these numbers instead. Now, depending on how the system is actually simulated and tested, there could be a slight variance of how the manufacturer actually rates something or what the actual test results are. Let's move on to some real-life examples and how to calculate peak torque based on a gear ratio at the wheel given any mid-drive. For instance, we have a 5th gen Bosch CX motor and a cassette with 11 to 42 teeth and a chainring at 34 teeth. In the lowest gear, it's going to produce 124 Newton meters of peak torque, and in the fastest gear, it's going to produce 32. And we can see this on a much more powerful motor, the same thing. In the lowest gear on the system, it's going to produce a whopping 346 Newton meters of torque, and in the fastest gear, 91. But our last example here is a hub drive which is directly laced to the wheel, so it does not use the bicycle gears to multiply the torque. Therefore, the motor at the wheel is 80 Newton meters, and in its lowest or highest gear, it's still going to remain as 80 Newton meters, because the gear ratio is 1:1. Now note, with some modifications, almost any motor can exceed its OEM peak torque rating. But that's going to depend on the specifics of if you can modify the ecosystem that the motor belongs to. Moving on to the relationship between torque and amps. The more phase amps you have being pushed to the motor from a tuned or aftermarket controller would mean more peak torque. above and over the OEM rating if the motor does not overheat, the controller, battery, and wiring is capable of providing the required current. The relationship between torque and amps can be measured using this torque constant, illustrated by KT, which essentially means Newton meters per phase amp, calculated at the rotor of the motor before any gear ratios. That's gear ratios on the bike or gear ratios in the motor itself. As long as you're within the motor's thermal and magnetic limits, the KT relationship is linear, meaning as amps increase, so does torque. For example, this CYC motor here has a KT of 0.089, taking the motor's peak torque and dividing it by the phase current. But in reality, this motor is producing more torque. Remember, it's a 280 Newton meter mid-drive. That's because the internal gear ratio of this motor is 36:1. So for every time that the chain rings turns once, the rotor is actually turned 36 times. Whereas the big MXUS hub drive has a KT of 1.28. Moving on to power. Electrical power in watts, as we know, is voltage, volts times current, amps. Whereas mechanical power in motors, watts, is torque, Newton meters times angular speed, or radius per second. Now, if you ever need to calculate this in motor RPM, RPM is equal to angular speed times this constant here. All what a motor is essentially a device that converts this electrical power into mechanical power by taking your amps and your volts and changing it to torque and speed. And also in the process producing heat, noise, and a few other losses, which we'll get to later. Back EMF. When a motor spins, it generates back EMF, standing for electromagnetic frequencies. Back EMF is motor voltage that opposes the controller supply voltage. Think of it like wrong-way traffic. It slows driver eagerness or voltage on the highway, aka motor windings, and as a result, the lanes close, reducing the number of cars taking that route, amps, proportionally reducing the total forward power, watts. Now, that's a bit to digest, but the short of it is the spinning motor starts acting as a generator pushing back against the controller. It's like a headwind when you're cycling. It's not notable at low speeds, but stops you from going any faster at a higher speed. Now, back EMF just opposes voltage, not current, but the lower voltage difference as the motor speed increases means the less current because of Ohm's law. For example, let's just say that the motor has no back EMF and there's 20 volts going from the controller and the motor has a 5 ohm resistance and there's 4 amps currently going through the motor. Whereas let's say the motor is spinning a lot faster now and there's 10 volts of difference, as in there's 20 volts coming from the controller, but 10 volts being pushed back, and we divide that by the same amount of resistance, and we only get 2 amps. So we can see back EMF directly opposes the voltage, but also indirectly affects the current. Just note that back EMF can be reduced with field weakening, and this is something that we go into detail when we cover controllers. But for now, let's look at the journey of back EMF as we increase speed of a motor. At a low motor speed or startup, we have a very low back EMF, and the effect on the motor is we have the highest torque and current flows freely. At a medium speed, the back EMF starts resisting the voltage from the controller, and at the highest speeds, the torque drops off as less current flows. And then at max speed, or this dotted line, the supply voltage becomes equal to the opposing voltage, meaning that there's no more acceleration, and our motor power is equal to our load, or in this case, our motor power plus our human input power is equal to load. And load meaning all of the resistances pushing back against the rider, aka friction, headwind, and all of those other factors. Now let's look at power, the conversion from electrical power to mechanical power over speed, as speed increases. In this simulation here, we have quite a powerful system and the throttle is at 100%. So think of it like a drag race. We are starting from a standstill and then we floor it. At the beginning of the drag race, we have the highest torque. The battery power is at maximum and the motor power climbs quickly as our speed increases. That's in this green zone here. So we can see in this graph, we've just launched. We're at 5 kilometers an hour, accelerating at almost 20 kilometers per hour per second, and we're pulling 10,000 watts from the motor. The torque at the wheel is 269 newton meters, but the motor power is only at 1000 watts because the speed is so low. Now we're at a medium speed at 25 kilometers an hour. The torque and the battery power begins to drop, and the motor power climbs slowly with the speed, and then eventually peaks. So we can see our acceleration went from 20 down to 12, and our battery power is decreasing from 10,000 to about 8,000, and our RPM is now at about 200, and our motor power is almost 4 times higher in terms of mechanical power, and the wheel torque has dropped from above 280 down to 179. So what this all means is the motor is catching up and turning that electrical power into mechanical power. And then finally, at our high speed zone, torque, battery, and motor power all drops as speed continues to climb, and eventually acceleration stops because motor power is equal to load, or resistances against the rider. We can see here motor power and load are effectively the same, and torque has dropped right down, and RPM is at its max, and acceleration is pretty much at a standstill, and the battery power has dropped right off where it's only a little bit higher than the motor power. So to once again summarize all 3 of these slides, the motor is converting electrical power into mechanical power, and as it increases in speed, it does a better job at doing so. Moving on to power ratings. Now, motor power ratings are massively misunderstood in the industry. Motors do not have a fixed power rating. Power depends on load, which changes, and the motor power limits actually depend upon the controller and battery output, and how much heat the motor can survive. So why do OEMs print the rated watts on motors like this? It's typically the continuous input power the motor can survive indefinitely, or to comply with legal standards set by various countries. For example, some places in the United States have a 750 watt limit, so that's what they stick on the motor. Even though most laws specify the max output power, or mechanical power, which is not the same as input power, as no motor is 100% efficient. So is a 750 watt rated motor better than a 500 watt motor? No, not always. There's no agreed upon industry standard to rate a motor, as in manufacturer A and manufacturer B might have a different process for rating power. Sometimes it could even be the same motor under the same or different brand, rated for different regions to comply with legal standards. Now, another couple of terms you may come across is nominal and peak. So nominal rated power is the power watts that the motor can continuously output, whereas peak rated power is the power in watts that the motor can briefly put out. Again, no agreed upon industry standards for these ratings, i.e. one manufacturer's peak output power rating could be 5 seconds, or another one could be 60 seconds before the motor overheats. So what's the actual rating? Well, if pushing the limits, it depends on how much heat the motor can survive. For example, my e-scooter peaks at 20,000 watts and has 2 3 kilowatt rated motors. In high power situations like this, using a temperature sensor in the motor is key, so the entire system can roll back the power if the motor gets too hot. Otherwise, you're usually safe if your controller output rating is lower than the motor power output rating. You can always go back to this motor simulator tool through this QR code, where it has many different motors where you can actually test and see how hot the motor may get under different scenarios. And briefly, let's discuss upgrades to the system. If you're considering upgrading an e-bike controller and battery, given the same motor, increasing the power will change these following variables. The more amps that you have, the more torque and acceleration you'll get, and heat. And the more volts that you put into the system, the more RPM and speed you'll get. So think amps, acceleration, volts, top end speed. Speaking of which, let's move on to speed. RPM means revolutions per minute. We know that the more voltage we have, the higher the max RPM. And if we wanted to calculate that, we can use these 2 formulas here. Each motor will try to spin at its max speed for a given voltage. This is measured with the constant kV. kV is affected by the motor winding design, or the turn count, which we'll cover shortly. kV is also inversely related to kT, which is the torque constant which we covered earlier. The more turns means the lower the kV and the higher the kT, which makes a high torque motor, and the less turns is the opposite, high kV, lower kT, or high speed. Now, if you want to see what that looks like, we have thin strands wrapped around or turned around the same stator tooth many times, whereas this one we have thicker strands where they are turned around the same stator tooth less times. More turns, less turns. Now, the goal to make a good motor is to maximize the copper infill, so the amount of conductor you can fit into these little stator slots. And you can do that by changing the gauge, the wire thickness, or increasing the strand count, or the number of wires in parallel. So here's an example of this going through our simulator. We have two different systems, System A and System B. They are identical in every way, except the motor itself has different turn counts, even though it is the same motor. On System A, we have a 5T motor, which has 12 strands wrapped around the same stator tooth 5 times. Whereas System B, we have a 3T motor, which is 21 strands wrapped around each stator tooth 3 times. The higher turn count system has higher torque, but that torque drops off faster, and therefore we have a lower top speed. Whereas the lower turn count system does not have the same initial acceleration, but has a higher top end speed. So here's a few key points. A motor's designed max RPM is going to be its kV times the voltage. Now the key word in there is supply voltage, and we know that can change depending upon back EMF and the speed of the motor. In a mid-drive, the wheel RPM is multiplied by the gear ratio of the current gear. As RPM increases, torque typically drops, and a motor can't spin faster when back EMF is equal to the supply voltage, unless we introduced field weakening, which we'll cover when we cover controllers. The motor's actual max RPM is when human power and the motor power is equal to load. RPM and load. So you've ever come across those videos or those scenarios where you see people hit full throttle when the bike is in the work stand versus when they're actually riding it. You'll notice the no load RPM when they're hooning it in the stand or lifting the rear wheel off the ground. The wheel spins freely and there's minimal load, which means the bike looks like it's doing 100 k's an hour. But in reality, you've got gravity and wind resistance when you're riding the bike, so the motor top speed is always going to be slower due to these forces. Think of load like towing a trailer. The more weight on the trailer, the more effort and therefore the more power that is required or drawn. In this analogy, consider the weight of the trailer to be a combination of all of those different resistive forces. Simply put, load is the forces that oppose you achieving max speed. If you want, you can pause the video here and go through each one in a little bit more detail. Now, one of the biggest forces is aerodynamic drag. It gets its own slide because to go 2 times the speed, you need 8 times the power, and that's just to overcome aero drag. For example, we have 2 different riders here. One is on an e-bike, they're just chilling out and they're going at 25 k's an hour. It only takes them 95 watts to overcome the aero drag, but if they wanted to go 100, it would take 6,000. Whereas you have a time trial racer, 26 watts versus 1,680. That's more than 3 times less energy they need to achieve the same speed because they're cutting through the wind like a knife. That's why you see a whole bunch of cyclists that use regular bikes without motors always cladded up in lycra and looking very aero. Because if they want to go fast and they're not aero, it requires a lot more power. Let's cover the relationship between load and torque. In this simulation, we have 2 different scenarios. System A and System B, they are going the same speed, but one of them is on a hill, and System A only needs 61% of their throttle, whereas System B, it's going full throttle to achieve the same speed. Now we can see here that even though we are going the same speed, System A only needs 8.9 Newton meters of torque to sustain that speed, whereas System B requires 25 Newton meters. And that is simply due to the hill. As we can see, the load is much higher when climbing the hill. Moving on to load and current, the controller increases the amps to meet the torque demand. So what's going on here? It's the same situation before, but both bikes this time are going full throttle, and they are maxing out the amount of power that they can pull from the battery, based on the limitations of the controllers. But since they are at their limits, the one on the flat can move a lot faster, whereas the one on the hill is struggling to keep up. Looking at load and acceleration, we have the same 2 bikes here. Both are going full throttle in a drag race and are both currently at 10.2 k's an hour, but one of them is on a hill. We can see the one on the flat is accelerating at almost twice the speed because the load is only 30 watts, whereas the one on the hill has 168 watts of load at the speed of 10 k's an hour. Simply put, the higher the load means the slower the acceleration. Moving on to efficiency. Motors don't convert 100% of that input power into mechanical power. Under ideal conditions, e-bike motors are typically 70 to 90% efficient. The rest of that energy gets wasted as a system loss, usually through things like the drivetrains. If you've got a dirty chain on a mid-drive, it can make it even worse. But the biggest losses come from inside the motor, which shows up as wasted energy as heat. Now you might think back EMF is also a system loss because it's fighting against the controller, but that actually makes the whole system more efficient because it's acting as its own generator, meaning the lower amount of power is required to continue spinning the motor at a higher speed. High efficiency is typically achieved at motor mid to high RPM when it's loaded, whereas peak efficiency is when torque and amps are low and RPM and back EMF is high. Here we have a real life example of a in-runner motor that's quite high power. This motor can cap out at around about 50 Newton meters of torque, and it's rated for around about 5,000 RPM, but it can be pushed further with field weakening. In the red is where the motor is most efficient, and in the blue is where it's least efficient. So as it accelerates, it gets more efficient as it reaches a higher speed, up until a certain point where efficiency will start to drop off again. Depending upon motor designs, the point of torque and RPM max efficiency may shift around a bit. Here's a couple of examples of different situations. The first one, we have no load max RPM, aka the e-bike is in the work stand and we're just flooring it for the fun of it. The torque is pretty much zero, the current is low and the work done is none, and therefore the efficiency technically is zero, because it's just overcoming the losses and not moving the bike. And then we have high loaded RPM, so we're riding full speed and there's no hill. The torque is moderate, the current is moderate, the work done is high, and the efficiency is peak. And then we have a low RPM under load, so we're going full throttle at launch and we're going full power up a steep hill. The torque is high, the current is high, and the work done is high, but the efficiency is low, due to the high load overpowering the system. Think of it this way, if you're on a regular bicycle and in your fastest gear and then you suddenly come on a hill, how difficult it is actually to climb that hill, as opposed to if you're in a very efficient gear and it is easy to climb the hill. Speaking of which, let's see how that actually looks on a mid-drive. In the simulation we have two identical systems, they are going full throttle and they are going up the same steep hill. The only difference is one of these bikes is in that wrong gear. And we can see as a result of that, the high torque bike, System A, may be moving slower because it's in a low gear, but it is running at a much higher efficiency of 82%, and the motor overall is running a lot cooler. Whereas in System B, it's moving faster technically, but the motor's spinning a lot slower and a lot of that energy is being wasted as heat. And we can see that the motor may overheat in just under 5 minutes. So that's why you can have mid-drives break or overheat when customers use them in the wrong gear. So to summarize efficiency, why is an efficient system important? Because it gets longer range, there's less heat loss, and you have better overall performance. And how to make a system more efficient? Having the correct gear or gear ratio and maintain all of the bearings, chain, and tire pressure or other things that may manifest as system losses. And lastly, we have temperature. Why do motors heat up? Well, mostly due to inefficiencies. Wasted electrical energy is heat. If a motor can't cool off, it may overheat, and they usually take time to heat up, so their damage might not be instant. All e-bike motors have an optimal temperature range. If they get too hot, basically what happens is the copper resistance increases and there's less torque per amps. You get possible demagnetization of the magnets between 100 and 120 degrees Celsius, depending on the magnet grade, and the motor may suck in moisture from the outside environment when it's cooling down. Basically, if a motor is sustained at this temperature, it may permanently reduce its performance due to that demagnetization, or could eventually short out with the enamel melting off the copper windings. The optimal temperature is 20 to 60 Celsius. It's the best efficiency, it's stable torque, current, and power, and minimal stress or losses. Kind of like e-bike batteries or humans. Room temperature to moderately warm is best. Now, if the motor is running slightly cool between 0 to 20 degrees Celsius, it might be just slightly less efficient, but that's not a big issue. If it's too cold, if the motor has a lot of internal gearings, the grease may thicken and the bearings may get stiff, which in turn increases mechanical drag. There can also be a condensation risk inside the motor from the motor heating up rapidly compared to the outside environment. But the performance of the bike will drop, and this is actually mostly coming from the drivetrain and the battery. To summarize this, hot, bad, optimal, great, too cold, not so much of an issue. Temperature in amps. In motor windings, twice the current means 4 times the heat. So the heat loss in watts is amps squared times resistance. So let's see what this looks like when we crank the power up on the same motor. The motor's resistance is staying the same because it's not yet overheated, and we start with 10 amps of input. So we're generating around about 12.8 watts of wasted heat. Double the input, it's 51 watts. Double it again, it's 200 watts. So looking at this graph, especially once we start putting hundreds of amps through a motor, we can see that it can produce a lot of waste heat very quickly. As a result, heat is the main bottleneck in high-performance e-bikes, motors, controllers, and batteries. There are useful cooling methods though, which we'll cover shortly. The correct design can also play a big part. For example, here we have 2 identical bike systems, but one of the motors has a slightly different turn count, and as a result, a slightly different KV, and also these hub motors are laced to different wheel sizes. The interesting thing here is they're going the same speed, the load is exactly the same, but we'll notice the change in temperature is only 1 degree Celsius above the initial 60 degrees, where it starts in the simulation, compared to System B, where it's an increase of 15 degrees Celsius. Because System A is actually more efficient, just because of the design choices of having a higher speed motor and a smaller wheel, means we get a dramatic reduction in the temperature. Because higher RPM equals higher back EMF, which means lower amps and therefore a lower temperature. Remember, with temperature limits, copper, magnets, and insulation all have safe maximum temperatures. That's typically 80 to 150 degrees Celsius depending upon the system. Exceeding this may result in reduced performance and permanent damage or motor failure. Going back to our example here, healthy looking coils and then overheated where the enamel has melted. Thermal rollback is a system where the controller reduces the amount of watts when a certain temperature is exceeded. The temperature may vary and may even cut power entirely depending upon the controller's settings. It's a great feature available on most modern e-bikes and advanced e-bike systems, which helps avoid motor burnout, but you don't typically see this on cheaper systems, resulting in stuff like this. A thermal rollback system just requires a motor with a working temperature sensor and a compatible wiring and controller. As in, is there a temp sensor wire heading to the motor, and does the controller have the function of thermal rollback? And here's a few various different cooling methods. This is more if you're looking at different high performance stuff. So what I've got here is the different cooling method: air, oil, ferrofluid, hub sinks, and water cooling, and then the different types of motors. A hub motor direct drive, hub motor geared, and mid drive. The different star rating is my own subjective rating on each system. To summarize this, basically for mid drives and hub drives, especially lower power e-bikes, sub 1000 watts, air cooling tends to be sufficient. If you're going for a more higher power system, ferrofluid and hub sinks together tend to be the best. But that's only if you're using a hub drive direct drive motor. It actually becomes close to useless in geared hub motors and mid drives. Oil cooling, which you'll see in high performance EVs, cars, and maybe some motorcycles, can work, but on e-bikes we find that it just tends to leak everywhere, and it's better to use ferrofluid because it sticks to the magnets and won't leak. Water cooling is another method. Again, that's something that you'd see probably on very high performance stuff. I have not seen a water cooled e-bike yet. In most cases, you're only really looking at 20,000 watts plus for water cooling. So to summarize, motor function is a big, hefty topic, but we can break it up into a few different key points. Torque comes from current. The more amps you have, the more torque you have. Speed comes from voltage. The more volts you have, the higher the top RPM. Back EMF limits the top speed, and it rises with RPM. Mechanical power in watts is torque, Newton meters, times the angular speed. Gear ratios multiply torque at the wheel. The more load equals the more current drawn, which in turn results in more strain and heat on the system. Efficiency saves power and reduces heat. Heat comes from losses. Manage it to protect the system. Click here to watch the next video. It is the best free thing you can do to tell YouTube to support the channel. Otherwise, if you want to do more, check out the links in the description. Thanks for watching.